Oi, we are back to the cosmic classroom. Today we are going to talk about the HR diagram. So if you look at the picture of the sky, or if you go outside in a very dark sky and look at stars, you'll notice that stars come in different colors, come in different brightnesses, and they also come in different sizes and different masses, something that you can't infer directly by looking at stars, but trust me, they do come in different sizes and different masses. So if you want to study a lot of stars together, like the stars in the picture that I just showed you before, you want to study them all together, what astronomers like to do as soon as they have a bunch of data is plot them. Let's plot and see what we can find. So the HR diagram is a plot that shows temperature in the lower axis, or color, which is also a measurement of temperature, or spectral type, which is also a measurement of temperature. And in the y-axis, it shows luminosity, or absolute magnitude, or apparent magnitude if all the objects are at the same distance from us. Those are all measurements of how bright the star is. Now, notice something funny here. The temperature increases to the left of this plot, contrary to what we usually observe when we plot things. Don't ask me why, it just is. All right? Astronomers like to do things in funny ways. There's something else that you should notice in this plot that's interesting. The colder objects are red, hotter objects are bluer, right? This is contrary to what you commonly think. You always hear that red is hot, like a red pepper is really hot. And, blue ice is cold. But in fact, objects become bluer as they become hotter. Just think about an iron that's heating up. As it starts to heat up, it is red. And then it becomes bluer. So as something gets hotter, it becomes bluer. You can also look at the flame on a candle. You'll see that the parts that are closer to where the flame is burning are bluer. They are hotter than red. So I can't tell you where does the idea that red is hot comes from, but I can tell you that in fact, blue light is hotter, has more energy, and it's what is emitted by hotter objects. So bluer stars are hotter than red stars. So let's move on and see what is it that we can learn from such a diagram. So first of all, let's look at two stars that have the same temperature. So those two stars have here the same temperature, and one is much more luminous than the other one. So notice that they may have the same size. All that's happening is that this one is more grayish, right? I tried to make it grayish. It's not really showing very well, but it's less bright than this one. That's what the y-axis is telling you. Faint, bright. The x-axis is telling you about the color. Blue, hot. Red, cold. So we have cold in this side, blue in that side. And now let's become a little bit more adventurous and see what happens as we look at two different corners of the HR diagram. If you look at the lower left of the HR diagram, you see objects that are blue, as read from this axis, and not very luminous at all. Now, if an object is blue, it should be pretty luminous because it's hot. But it's not. That means that this object is very small. Those objects are called dwarfs, dwarf stars. They are tiny because they are hot and not very luminous. Conversely, on the upper right corner of this plot, they are very large stars. Why? Because they are red, therefore they are not very hot, shouldn't be emitting a lot of light. But if you look at the y-axis, they are super luminous. Well, they must be huge then if they are not very hot. However, but very luminous. So those are the giants, the super giants in this plot. Okay, stars can be found in the different regions of this diagram. As you see here, most of the stars are found in this this diagonal line here, which is called the main sequence of stars. That's where stars spend most of their life. They spend 90% of their life there. Stars stay in this location when they are fusing hydrogen into helium in their cores. As they die, they move away from this main sequence and they become giants and then they become dwarfs. Because they live 90% of their life in the main sequence, you find 90% of the stars in the main sequence. Okay, one way that the HR diagram allows us to study things in astronomy is we can use it to measure ages of clusters. So stellar clusters, open clusters or globular clusters, are formed when a big cloud of gas collapses and forms many stars. So all of the stars in a cluster have the same age. All of the stars in a cluster are also at approximately the same distance from us, which allows us to say that if this star looks brighter than this one right there, it's because it really is. It's not because this one is closer than that one, because they are about the same distance. So if we get each one of those stars and we measure their color and measure their luminosity and we plot it in an HR diagram, we'll see the main sequence and we'll see something funny happening here. So let's focus first at M67, which is the cluster that I just showed you before. M67 has a main sequence of stars, but it doesn't have bluer stars here. The bluer stars in the main sequence are missing. They are missing because they died already. Big, massive blue stars. They live very bright, but they die young. They use their fuel very fast. So all of the stars that were very big and very massive and very blue have died already and cannot be found. They have moved to other places in the diagram. Therefore, by just looking at where the main sequence ends, and by knowing what kind of star is dying right now at this time, we can estimate the age of M67. We know then that all stars that live less than about 4 billion years have died already. We can't find any of those, meaning that that's the age of this cluster. Now we can compare it with another cluster, NGC 188. So notice that in NGC 188, all of those stars that are still alive, you're still in the main sequence in M67, are missing. Therefore, this cluster has to be older, has already lost more stars. And this cluster is indeed about 6 billion years. So we can use the HR diagram to measure ages. We'll see the HR diagram in many things in astronomy when we study stellar evolution. I hope this helped clarify some of the questions that you had on the HR diagram. See you next time.